In Chapter 4, we'll continue with our study of statistics by looking further into displaying and exploring our data. If you want to review the objectives for Chapter 4, please review the first portion of the Chapter 1 video where I give you the objectives for the chapters 1 through 4. We briefly looked at some of the methods of displaying our data with a pie chart and frequency tables. So we're going to start off with a dot plot in this chapter. And the dot plot groups the data together in little space as possible and still keeping the identity of each individual observation. In other words, we have this list of observations here. Each of these dots indicate one observation. And for this example, it's the age of the Applewood Auto Group buyers. And all we've done is we've taken each age and put them on a more or less a number line of ages ranging from 20 to 60. So we've had one person who was 25 years old, one person who was 26 years old, then we have 27, 28, so we have two people that were 28, two people that were 29, and then we go on through all of the different ages that we have observations for. If you look, they're stacked up, and you can look across quickly and see that our two highest points appear to be at 46 and 51, and we can count those 1, 2, 3, 4, 5, 6, and we find that we have 6 observations at 46 and 6 observations at 51. This also should pop in your mind as a bimodal distribution. So the frequency count for 46 years old and 51 years old each are 6. So we have 2 modes in here. But that's an aside. The important point to note here is that we have in this number line, in this dot plot, every observation in our data set. Now imagine though if we were doing this on the age of all students who attend XYZ University. Well, we would have thousands of ages, and they would be probably pretty closely grouped around in this area here. You'd have, of course, outliers up in here, maybe even a few below 20. Well, definitely you'd have some below 20. But it would be very difficult to distinguish how many we have because the plot lines would be very, very tall, especially around the ages of 20, 18 to 22. The point is that dot plots are useful for small data sets, and when you have larger data sets you might want to look at another form of data representation. But looking here, we can see what's the youngest age of an auto buyer that we had at Applewood Auto Group buyers. Well, we can look and we can see quickly that it's 25, and the oldest buyer was 58. And if you want to look further, you can see the video here on how to do a dot plot using the Excel and Megastat. If you remember back in Chapter 2, we used a frequency distribution to organize the data into groupings of values. And the advantage of that is that it gives us a quick visual picture of the shape of the distribution. However, there's a problem with doing that. We pointed that out before, was we lose the individual observations in the data set. In other words, we don't get to see the actual values of each individual observation. And the other part is that we don't get to see how the values are distributed within the grouping. Remember, we had the grouping, we had 8 observations in the grouping age from, let's say, if we were to use our grouping here, we would have the age group of 25 to 30, and we would have a total of 2, 4, 6, 8 observations in that age group. And if we used a frequency distribution, we'd see in the range of 25 to 30, we'd have the range or the values 8 observations in there, but we wouldn't be able to tell the granularity that we see in the dot plot. So with the stem and leaf, similar to a dot plot, we get to see the granularity or the observation of in each individual data element. And one way we can do that with the stem and leaf is to provide the statistical technique to present the set of data And if you want to see a further or greater detail of that, you can look at the video that we have listed here in the YouTube or the Excel example highlighted area up here. But essentially how a stem and leaf works is your values or your observations are divided into a stem and then the leaf section. The leading digits are the stem, and in this case we're talking about the tens place, so this would be 80, 90, 100, 110, and so on down the line. And then our leaf is the individual place or the trailing digit of the leaf. And in the leaves you can see that we can have multiples of a particular observation value. So we can see that in the stem of 9 we have a value of 96, another value of 96, a value of 94, another value of 94, a value of 93, a value of 95, and then a value of 97. Frequently you'll see these where the values are organized chronologically. So you would actually see 3, 4, 5, 6, 6. Oh, excuse me. It would be 3, 4, 4, 5, 6, 7, 7. And again, the advantage of having the stem and leaf over a frequency distribution is that we get to see each observation and the identity of each observation, much like we do with the dot plot, but in a tighter compartmentalized view. As we looked at in the last chapter, we use standard deviation to determine the spread of the data set. And the standard deviation is the most widely used measure of dispersion. Another way of describing how the data is spread out, it includes using the location of values to provide a division marker for a set of observations, and we break it into equal parts. You may be familiar with some of these divisions, such as percentiles, quartiles, or deciles, and they could really be any measure of division that we choose to use, but those are some commonly used methods. If you want to look in detail at how to calculate the percentile, I have a video listed here that you can link to gather that information and observe how to calculate the percentile. But essentially here's the calculation, where L is the location and L sub p is the location of the percentile that we refer to. And when we do a percentile, what we're doing is dividing up our data set into 100 parts, and then we calculate a location based on whatever percentile we want. So if we wanted the median, which is the middle point, we would go to the 50th percentile, and that would be denoted as L sub 50. And our calculation is that we would take our L sub p equals n plus 1 times p divided by 100. So if we want the 50th percentile, we would put p, or 50, over 100, which would be a half, multiply that by n plus 1, and then we would get our location of the median, or the 50th percentile. We can convert this formula to determine quartiles by changing the 100 to a 4 in the denominator and going from there. A box plot now is a graphical display, and what that graphical display is built off of is quartiles. So it helps us to get a picture of a set of data. And to construct the box plot, you need 5 statistics, the 5-number summary as it sometimes is referred to. We need the minimum value of our data set, the first quartile, the median, or second quartile, or 50th percentile, depending on how you want to look at it, the third quartile, and then the maximum value that's not an outlier. To see a video on how to create a box plot, you can refer to the YouTube video links that I have up here in the right-hand corner. The steps to create a box plot are: Step 1, create an appropriate scale along the horizontal axis. Step 2, draw a box that starts at Q1, or the first quartile, and ends at Q3. So the range of the box is from first quartile to the third quartile. and inside the box we place a vertical line to represent the median, or the Q2, or the 50th percentile, depending on how you want to look at it. Then we extend horizontal lines from the box out to the minimum value that's not an outlier and the maximum value that's not an outlier. And based on that, we create the box plot, sometimes referred to the box and whisker plot. So from this, we can conclude, since these are pizza delivery times in this example, we can see that the shortest pizza delivery time was 13 minutes, and the longest was 30 minutes, and the median time was 18 minutes. And on the next page, I've provided a reference page that gives you a lot of information about the box and whisker plot, or the box plot. I encourage you to take a look at that to get a better understanding of what information you can gain from a box plot. Earlier, we talked about measures of central tendency, measures of the mean, the median, and the mode. And I told you that there were three things that I liked to know about every data set that I had. Do you remember what those are? They were the measure of central tendency, the dispersion, and the shape of the distribution. So we talked about the measures of central tendency, the mean, the median, and the mode. And we talked about dispersion, where we talked about range, variance, and we talked about standard deviation. Well, now we're going to talk about skewness. We briefly touched on that earlier, but another characteristic that we can go into greater detail on about the data is the shape, as we were talking about that. And there are four shapes that are commonly observed: the symmetric, positively skewed, negatively skewed, and bimodal, which really should probably read multimodal. Although we don't usually have quite as many that have multiple modes in there. And if you remember back in our conversation in chapter 3, we talked about the tail being pulled to the left for a negatively skewed, and the positively skewed would have the tail of the distribution pulled to the right. But there's actually a calculation that you can do to determine the skewness, and that formula is right here. There's the Pearson's coefficient of skewness, and then the software coefficient of skewness. Now the Pearson's coefficient of skewness, as you can see, is a less complex calculation, or less complex formula to calculate. And this is perfectly acceptable to use if you want to manually calculate the coefficient of skewness. Some software programs will have a much more complex calculation that you can see in the software coefficient of skewness. And some characteristics of skewness are that it can range from a value of -3 up to +3. A value near -3 indicates considerable negative skewness. A value such as 1.63 indicates moderate positive skewness, and a value of 0 should ring a bell to you. That's when the mean, the median, and the mode are all equal, and it indicates that the distribution is symmetrical and there's no skewness present. And we can take a look at these distributions and some commonly observed shapes that we might see. So here's a symmetric, and this is a little bit off, and it's difficult to create these graphics perfectly accurately, but a normal distribution doesn't actually touch there. It's called asymptotic, meaning these lines go out through infinity without ever touching the x-axis. So just visualize that this does not actually touch, even though it does clearly touch in the picture. And if you remember from our chapter 3, when the tail is pulled to the right, as it is here, it's positively skewed. When the tail is pulled to the left, it's negatively skewed. And here's an example of bimodal. And you could figure that these two would actually be connected still, because the distribution would be a single distribution. It would just happen to have two modes to it. And as you can see here, we have another example that you can watch in the YouTube video on how to calculate out the skewness. Now my slides go out of sequence from what your slides have, because I just rearranged them, because I find that this was a better way to explain the empirical rule and Chebyshev's theorem. So the empirical rule is a rule for the normal distribution. It's a symmetrical bell-shaped frequency distribution. In other words, it's symmetrical. The mean, the median, and the mode are all the same. And it means that approximately, or about, 68% of all observations can be found between -1 standard deviation and +1 standard deviation. So about 68% of all the observations are in this area right here. Also with the empirical rule, sometimes called the normal distribution rule or the normal rule, 95% or about 95% of all observations will fall between -2 standard deviations and +2 standard deviations. In other words, in here. And then finally, about 99.7% of all observations lie between -3 standard deviations and +3 standard deviations. We use that information when we're doing our statistical analysis to determine about how much we should expect to see in a certain area. So if we had a normally distributed data set, in other words, it was symmetrical bell-shaped, just the way we see it here, and we saw an observation that was beyond 130, it was way out here, maybe 200, so that would put us somewhere way out in this area here. We could look at that and we would say, does that seem unusual? Well, in this case, when we have nearly 100% of all of the observations lying between -3 standard deviations and +3 standard deviations, and we found a value way out here, we could then look at that and say, wow, that seems to be a little bit unrealistic. You don't have to say the wow part, that's just optional. So this comes in handy when we're doing other types of analysis within the field of statistics. But again, it relies on the distribution being symmetrical in order to do that. So what happens if we don't have a symmetrical distribution? Well, that's where the Chebyshev's theorem comes into play. And you might see this spelled with a C here instead of an S, but it's talking about when you have a non-symmetrical distribution or an odd-shaped distribution, you can calculate what proportion of the values lie within a certain number of standard deviations from the mean, or at least a certain amount will fall within that range. So you may get more, but at least a certain amount will fall into that range. But again, that's just here as a reference page. We usually rely on the normal distribution and the empirical rule when we're doing our hypothesis testing, which we'll get into later. So let's take a contrasting look at the two. On the left, we have a normal distribution, and again, we have -1 standard deviation to +1 standard deviation is 68% of our observations, and the two tildes there are indicating that it's about 68%, and then plus and minus 2 standard deviations is about 95%, and plus and minus 3 standard deviations is about 99.7% of all observations lie within those ranges. Here, with the Chebyshev's calculation, it's not perfectly distributed, symmetrical, as we saw with the empirical rule, but we can calculate that within 2 plus and minus 2 standard deviations from the mean, we have about 75, or at least 75, I should say, not about, at least 75% will fall within there, or the observations will fall within that. And at least 88.89% will fall within -3 to +3 standard deviations. But again, we're going to focus mainly on the empirical rule, and just keep in mind that Chebyshev does exist. Up until now, we've been talking about looking at data sets of individual variables. And what do we want to do if we want to show a relationship between two variables? Well, one of the things that we can do is we can use a scatter diagram or a scatter plot to show the relationship between two variables. When we study the relationship between two variables, we refer to the data as bivariate. And using a scatter diagram, we can put one variable on the x-axis and one variable on the y-axis. And I have an example on YouTube, no surprise there, that you can use to see how I build a scatter diagram with two variables. And here are examples of scatter diagrams, and you can see the relationship. For example, here this is a scatter diagram of age of buses and the maintenance cost, and we see as the age increases or the buses get older, the cost to maintain them increases. And that's what we call a direct relationship. On the other hand, in the auction price versus odometer scatter plot, we can see that as the odometer reading on the car increases, the auction price of the car decreases. That's an inverse or indirect relationship. The other thing that we can see is that in this scatter plot, the numbers or the observations are close together. They're tightly related. Here, they're not as tightly related or associated, and we call that the correlation and the strength of the relationship. We'll get into that further on in the class. But in this example here, we have height versus salary. Generally speaking, there's no relationship between the height of a person and the salary that they earn, and that's why we see our plot is all spread out and dispersed all over the table or the chart. In order for us to do a scatter plot, we need to have interval or ratio level data. It has to be at least interval level data in order for us to do a scatter plot. What happens if we don't have that? Well, we can turn to a contingency table, and a contingency table is a cross tabulation that simultaneously summarizes two variables of interest. We've seen cross tabs when we've done our pivot table examples, and it's just a way of categorizing our data in order to look at it and identify different characteristics from the data. And really, when you think about it, all of our descriptive statistics that we use are just a means to make heads or tails of our data, because if we threw up a lot of values onto a dry erase board, it would not make a lot of sense unless we put some kind of structure to it. Contingency tables are just another structure that we can put to our data. And here's a reference page for how to do a contingency table, but we're not going to get into that for this exercise. You can use that video as a reference if you want to go through that exercise in doing the contingency table creation. And this concludes our lesson in Chapter 4 of the Lind text.